All right, let's go back to the beginning of our unit and just real briefly define the terms, redefine the terms that we've already defined so far in the unit. The first one was frequency. Frequency given by the symbol lowercase f. Big F is force, small f is frequency. Frequency is defined as what? How many times per day do you have physics class? The frequency of physics is once per day. The frequency of physics is also 5 times per week. Okay, the frequency of classes in general is 4 times per day. The frequency of bells, okay, is once per period, once per class. Okay, the frequency is the number of events per unit time, or in the context of circular motion, the number of revolutions per unit time. Now, normally that unit time is going to be what? We could say the number of physics classes per day or the number of physics classes per week, but normally we're going to say it's the number of events or the number of cycles per second, right? The number of cycles per second. Now, if we're going to define it as the number of cycles per second, then our equation can quite simply be the number of cycles divided by the total time. The units for frequency would be cycles per second, but we usually abbreviate that with the symbol Hz, which means hertz. 1 cycle per second or 1 revolution per second is equal to 1 hertz. Period is the next one that we looked at. It's given by the symbol capital T. Don't get that mixed up with just any time. Time is T. Period is lowercase t as well. In the end, lowercase t represents any time, but specifically the period can be represented by capital T. So if we want to be specific as to what our time means, and it happens to be the time for 1 complete cycle, 1 complete revolution, then we're going to go with a capital T. We're going to say it's the time for 1 cycle, or in this case, the time for 1 revolution. Now, the equation for that is going to be the exact opposite to that of frequency. Instead of being cycles over time, it's going to be the total time divided by the number of cycles. Units? Usually we just go with seconds, although you could also say seconds per cycle or seconds per revolution. These two equations don't appear on our data sheet, but there is an equation that relates the two together that does appear on our data sheet. What is that one? T is equal to what? Yep. Yeah, T is equal to 1 over the frequency. That one does appear on our data sheet. The next thing we talked about was speed. We know that if something's moving at a constant speed, it can be represented by the equation V is equal to delta D over delta T. And of course, we're always talking in this unit about objects going at a constant speed because we're talking about uniform circular motion. That's what uniform circular motion is, an object moving in a circle at a constant speed. So we can use this equation D over T, but we can get a little bit more specific. The distance around a circle once represents what? Yep, circumference. And the equation for circumference, somebody else? The guys who gave it to me the other day, I think it's pi times d. Okay, that's correct. If you want to use that, go ahead, but it's not the way it appears on our data sheet. What's the way that it appears on our data sheet? V is equal to 2 pi r, right? The circumference of the circle, the distance around the circle once is 2 pi r, the circumference. The time around the circle once is t, capital T, the period. That one appears on our data sheet as well. Yesterday, we started talking about centripetal things, centripetal acceleration and centripetal force. You guys remember what the word centripetal meant? Centripetal means center seeking. So an acceleration that seeks the center, an acceleration that points toward the center of a circle. How can we get an acceleration here? If we've got an object that's in uniform circular motion, in other words, traveling at a constant speed, how can we say that it's accelerating when it's not changing speed? Something's changing, but it isn't speed. Good. The direction changes. Now, the direction changes doesn't mean it's speeding up or slowing down, but the direction changing means that it is changing velocity, because velocity is a vector and it includes direction. As long as the velocity is changing, the speed doesn't have to. We still have an acceleration. Now, that centripetal acceleration, given by kind of an odd equation, A is equal to v squared over r. What's v stand for? Speed, not velocity. Okay, not velocity. The velocity is changing. We can't plug velocity into this equation. It's not staying the same. Speed is staying the same. We can therefore plug it in as whatever it is. R stands for the radius of the circle. And what units is radius going to be measured in? Speed in meters per second, R in meters, right? Why do we have those little vertical lines on either side of the A? Yep. Good. Absolute values. Absolute value just means that when we solve for this AC, we're not going to get the direction of the acceleration like we usually do in an equation. This time we're only going to get the magnitude. But that's okay, because we always know the direction is toward the center of the circle. We don't need the direction. We know what it is already. It's pointing toward the center of the circle. The last term that we looked at yesterday was centripetal force. The centripetal force is the force that points toward the center of the circle. Force is equal to m times A. But A is v squared over r. So centripetal force will simply be m times v squared over r. Both of these equations appear on our data sheet. Don't have to memorize either one of them. Just know what they mean. Now, we said yesterday centripetal force isn't a fundamental force. What does that mean? What did I mean by that? It's not a fundamental force. It's not a force that acts on its own. It's got to be caused by something. Centripetal force is really just renaming another force. If the Earth is going around the sun, okay, the force that keeps it in orbit is called gravity. That gravitational force, we can rename centripetal force if we want, because it's a force that keeps something going in a circle. The case of my keys going around my head yesterday, okay, we can rename the force of the string the centripetal force if we want, because in the end, that force is acting toward the center of the circle. A car going around a turn, it's kept going around the turn by friction. That frictional force, we can rename the centripetal force if we want, because of course that force is acting toward the center of the circle. So centripetal force can be represented by this equation no matter what causes it, but it can also be represented by another equation depending upon which other kind of force is causing it. And we'll see about that as time goes on. Okay, situations where we can use either equation, this one or another equation. All right, we had a little bit of homework last night, page 255. 3 questions. Any issues with those 3 questions on 255, please? Yep. Number 3. Two. We got 2 and 3. All right. Number 2 says a child playing with a top spins it so that it has a centripetal acceleration of 125 meters per second squared at the edge, a distance of 3 centimeters from the axis of rotation. What's the speed of the edge of the top? In question number 2, the centripetal acceleration is 125.0 meters per second squared. Something's 3 centimeters. What is that? Yeah, it's the radius. Now, we got to convert that to meters, right? We don't want centimeters. 0.0300 meters. We want to find the speed. Well, up until yesterday, to find the speed, you would have said v is equal to 2 pi r over t. But I don't have any information about t, the period, how long it takes this top to make one spin. So it doesn't look like that one's going to work for me. As of yesterday, I have this equation with speed in it. Since I have r and a, looks like that one's going to be the one that I use. Let's take the r out by multiplying. And then how do you get rid of the square? Square root it. So it becomes v is equal to the square root of a times r. So let's do that math now. A is 125. R is 0.0300. Let's square root that. And when we do that math, we should end up getting 1.94 meters per second. Now, that might not seem like a very high speed, right? It's not. It's not a huge speed. But if you're talking about a spinning top, right, its radius is pretty small, right? 3 centimeters. If the outer surface of that tiny little spinning top is moving at almost 2 meters per second, it's still moving pretty quickly, right? It's going by you pretty quickly. Okay, if the outer surface of that is moving at 1.94 meters per second. If you had a big, merry-go-round, the outer edge of it is moving at 1.94, then that wouldn't be very fast. But if it's close to the center, it's going to still make a lot of revolutions per second if it's going at 1.94 meters per second. All right. 3. A helicopter blade has a diameter. I don't like that. Why not? I want radius. Okay, Jazzy gave me the equation for circumference with diameter in it, and that's fine. If he's going to use that, then he can use the diameter. I'm not going to, because that's not the way it appears on my data sheet. I'm going to go with radius, and I'm always going to go with radius. I'm going to actually draw attention to this. Put a little star by it or something to remind me that that's not the number I want. Although I can get the number I want pretty easily. Okay, this isn't it. We have an acceleration of 2527 meters per second squared. What's the period? We're going to say R is 7.00 meters. We're going to say A is 2527 meters per second squared. We want to find T. The only equation we have with period in it, besides 1 over F, is V is equal to 2 pi R over T. Rearrange that, 2 pi R over V. My problem with this one is that I don't know what V is. So let's find it. Let's say A is equal to V squared over R. Let's solve for V. Same as we did in the last question. So it becomes the square root of 2527 times 7. Anyone have the value for that speed? 133.0. Is it exact? Okay, 133 meters per second. Thank you, Kathleen. That's pretty fast, right? You got the outer edge of this helicopter blade moving at 133 meters per second. In other words, a single point on the edge of that helicopter blade, if it was traveling in a straight line, would go about 1.5 times the length of the football field in 1 second. That's why you don't want to stick your hand up there and try to hold onto the blade as it's spinning around, because it's going to cut your hand right off instantly. 133 meters per second. All right, now let's find the period. It becomes 2 times pi times 7.00 over 133. Do the math on that one, it should work out to be 0.331. So even though it's 14 meters from one side of one tip to the other tip, 14 meters is quite a distance. It still makes a complete revolution in less than 1/3 of a second. It takes the blade less than 1/3 of 1 second to go all the way around once. Okay, well, it goes pretty quickly. We know that because the speed of it was 133 meters per second. We good there? Got another one to do here right now. 5.4 on 256. This one says, determine the magnitude of the force on the rim of a dragster's wheel by the rim of a dragster's wheel on a 45 kilogram tire. If the tire has a 0.480 meter radius and is rotating at a speed of 30 meters per second. Centripetal force this time. Right? We're not looking for acceleration, we're looking for force. My mass is 45.0 kilograms. My radius is 0.480 meters. Gentlemen? My speed is 30 meters per second. Okay, this is pretty straightforward, right? Look, if you can find the acceleration, you can find the force. mv squared over r. 45.0 times 30 squared. Hey, I've got this drawn as m times v squared over r. What if I do this? How does that change things? M times v squared over r is the same thing as saying mv squared all over r. It's the same thing, isn't it? It doesn't matter which way we write it. It means the same thing. Okay, let's calculate that. Let's take our calculator out to do it. Let's take 45 times 30 squared. Divide that by 0.480. You get 84,375. 8.44 times 10 to the 4 newtons. Good? How many people are kind of into cars here? Yeah? So you can buy tires that are rated for certain speeds, right? The higher speed they're rated for, the more you pay for the tire, right? Most people don't need tires that are rated for 240 kilometers per hour because you're not going to travel 240 kilometers per hour. But you can buy them. Why are different tires rated for different speeds? Why aren't they all the same? Why does it matter how fast you're going? Tire's a tire, right? As long as it fits on the rim, shouldn't they all be the same? Well, the faster you're going, the bigger the centripetal force required to keep the tire together. Right? The tire is going to disintegrate after a certain centripetal force. You need a bigger centripetal force with a bigger speed. In fact, it goes up exponentially. As v goes up, F goes up by a factor of v squared. The faster you go, the stronger the tire needs to be. Why do you pay more for tires that are rated at higher speeds? Because they got to be built stronger. They're better tires. It costs more to make those tires than it does to make the ones that are rated for, 170 or whatever the case may be. All right. Let's have a look at these two questions, please. We'll see how those ones go for you. We'll take a look at a couple of them if we need to in just a few minutes. All right, we'll take a look at number 2. It says a 0.0021 kilogram pebble is stuck in the treads of a dirt bike's wheel. The radius of the wheel is 23 centimeters. We don't like that right away. We want to draw attention to that because we know we're going to make that in meters. Centripetal force, 0.660 meters. What's the speed of the wheel? All right, question number 2, M is 0.0021 kilograms. We know that the radius here, is 0.230 meters. And the force, the centripetal force, is 0.660 newtons. That's going to give me a speed of, so we're trying to find. So we're going to say F is equal to mv squared over r. Let's solve for v. It's a little bit tricky. Take the r up by multiplying. Take the m down by dividing. And how do we get rid of the squared? We're just going to square root it, right, Joe? So we're going to say v is equal to f times r over m, and then we square root that. So we get square root of 0.660 times 0.230 divided by the mass. Get a number for that, then square root it, and I think when we do that, we should get 8.5 meters per second. We good? Make sense? So this pebble is stuck in the treads of the tread of the dirt bike's wheel. This wheel spins around at the outer edge at 8.5 meters per second. There's a centripetal force acting on the pebble that is 0.660 newtons. If the pebble became a little loosened and the tire couldn't supply that much centripetal force because maybe that little tread was a little bit wider and whatever, it wasn't stuck in there quite as much, what would happen to the rock? It would shoot out. Because if you can't supply enough centripetal force to keep it moving at that speed and at that radius, then what's going to happen to it? It's going to go off in a straight line, and the pebble is going to go flying, right? Make sense? Okay, we got one more. Oh, I like this one. All of a sudden, we've got friction added into here. Determine the maximum speed at which a 1,500 kilogram car can round a curve that has a radius of 40 meters if the coefficient of friction between the tires and the road is 0.6. What? What force acts on every object moving in a circle, whether it be a car going around a turn or whether it be the Earth going around the sun? What's that force called? Javi? No. Inertia is the tendency to keep it in a straight line, right? The tendency to resist the change in motion, so to go off in a straight line. It's the exact opposite of that, right? What keeps it from going in a straight line? What keeps it going in a circle, Jazzy? Centripetal force, right? There's a centripetal force here. But we said that centripetal force is never a fundamental force. It's always caused by something. In the case of swinging the keys around my head, it was caused by the string. In the case of the Earth going around the sun, it's caused by gravity. In the case of a car going around a turn, it's caused by friction. So what we're going to do here is set Fc equal to Ff. Right, if centripetal force is caused by friction, then they've got to be equal to each other. That means that mv squared over r, the centripetal force, is equal to the force of friction. That's mu times the normal force. What's the normal force on a flat surface? No, but close. It's about m times 9.81, right? Mu times the normal force, m times mu times m times g. Now, we got the mass of this car here, but notice, since it appears in both terms, we can cancel it if we want and not even use the mass. What does that tell you about a car going around a turn? Doesn't matter what the mass is. Okay, it doesn't matter whether you've got one person in the driver's seat or 4 people or 5 people in the car. It doesn't matter whether you've got a smart car or you've got a 1973 Chrysler New Yorker that weighs about 6 tons. The maximum speed will be the same. Now, there's different handling issues with different vehicles, right? So that's going to play a factor. But in terms of pure friction, it doesn't matter how heavy the car is. As long as you have the same tires, it doesn't matter. Okay, we're going to solve for speed here. So let's take the r up by multiplying. It becomes mu times g times r. And then let's square root that. Square root of 0.60 times 9.81 times r, 40 meters. Let's solve that now. Let's say 0.6 times 9.81 times 40. Let's press equals, and then let's square root that. And we got 15.3 meters per second. We're going to round that to 15 meters per second. So you go 14 meters per second, what's going to happen? Well, the centripetal force provided by friction is strong enough to hold you in the circle. If you go 16 meters per second, well, the centripetal force that can be provided by friction isn't big enough. So what happens to you? You go off the road, right? You slide off the road. What happens if we introduce ice onto this turn? You got to go a lot slower, right? Why? The coefficient of friction is a lot lower. And if the coefficient of friction is a lot lower, the force of friction is a lot lower. Therefore, the maximum value of centripetal force that can be provided is too low to keep you in that circle. Got to go slower. Try these ones. All right, everyone, let's finish those questions on those practice problems that we were just working up for homework. If you haven't finished them already, let's talk, for the last thing for today, about something called centrifugal force. Now, let's differentiate that with centripetal force. You've heard both of those words before, centripetal and centrifugal. Centripetal means center-seeking. We talked about that yesterday. We talked about it earlier today. Center-seeking. In other words, a force that pulls something in toward the center. Centrifugal means center fleeing. So in other words, a force that pushes it out from the middle to the outside. You guys have all experienced that before, right? The centrifugal force, the force that pushes something to the outside of a circle. Notice I have force in quotation marks there. The reason that I put a force in quotation marks there when we're defining centrifugal force is that it's not really a force. There is no such thing as a force that pushes an object towards the outside of a circle. Well, that doesn't make sense, right? You guys have all experienced that. You got four people in your little, Honda or your little Honda Civic. You're going around a corner really, really fast. What happens? They all get pushed to the door, pushed against the door, right? You get pushed to the outside of the circle. You're on that ride at Callaway Park. I can't remember what it's called, but it's that green spinny thing. You all get pushed against the outside of it, right? You guys have all felt that before, right? That centrifugal force that pushes you to the outside. I'm telling you, it doesn't exist. It doesn't. There is no such thing as a centrifugal force. It is fictitious. It's what we call a pseudo force. It doesn't exist. Well, how do you feel it then if it doesn't really exist? Let me give you another scenario here, okay? I'm going to sit in my seat here, and I'm going to pretend that I'm sitting in the driver's seat of my car. Somebody comes up behind me and hits me from behind. What happens to me? Well, my head goes back, right? Well, we know it doesn't really go back. When we talked about Newton's first law, we know that my head stays at rest and my body goes forward, right? What does it feel like to me? It feels like to me that I'm being pushed against my seat, right? Am I being pushed against my seat? No. My seat is being pushed against me. I'm accelerating forward as my seat pushes me forward. But what does it feel like to me? It feels like I'm being pushed back into my seat. Whenever we have an acceleration in the context of circular motion or any other acceleration, we get what we call a pseudo force. It's a pretend force, a non-existent force, a fictional force that acts opposite to the way the real force acts. So when I'm being pushed forward, it makes me feel like I'm being pushed backward. When I'm being pushed to the center of a circle, it makes me feel like I'm being pushed to the outside of the circle. Does that make sense? So can anybody explain to me why, if I was on a merry-go-round and I let go, okay, why I would actually be kind of thrown outwards? Okay, why if I'm on spinning around, okay, here's the bars of the merry-go-round. I'm spinning around on the bars of the merry-go-round. When I was in elementary school, you don't see merry-go-rounds very often anymore because, I don't know, too many kids get hurt and sissies, I don't know. I love merry-go-rounds. We had a merry-go-round when I was in elementary school 35 years ago. We used to love to play on that thing. We'd get that thing spinning so fast. I know that kids, every year there was kids that broke their arms off of that thing because you get that thing spinning so fast, the kids would start flying off the end because they couldn't hold on anymore, right? They needed such a centripetal force provided by their own muscles to keep them on that they just couldn't provide it. They just couldn't do it. So they flew off and they hurt themselves. It was fun though, most of the time. If you found yourself holding onto the bar right here and this thing was spinning around really, really fast, you couldn't help it. You ended up going to the outside. If it's a fictitious force, a force that doesn't really exist, if it's just a force that we think exists, it feels like it exists, how do we actually go to the outside? Are we just kind of creeping out to the outside because psychologically we think we're supposed to? No, we do go to the outside, but it's not a force that pushes me there. Here's what happens. Here's the pivot point. Here's the rotational point. I'm right here, okay? I'm going in a straight line, right? I'm always going in a straight line. If I'm not holding onto this bar tight enough, then I'm going to go in a straight line. Here's the merry-go-round. Here's the bar of the merry-go-round that I'm trying to hold on to, but I can't hold on to tight enough. That bar of the merry-go-round is turning around this way. By the time that bar of the merry-go-round is over here, I've gone in a straight line. Where am I? Holding on to the end of the bar. Does that make sense? So what it really is, me being pushed to the outside is really my inertia taking me in a straight line and then me catching up with the end of the bar. Now, the reality is, yeah, we should really draw about 1,000 different stages between here and here, because you're not literally going in a straight line all the way from here to here, but it's that idea. Okay, you're not being pushed to the outside along that bar, you're going in a straight line, and then by the time you catch up with the end of the bar, you've gotten to the end of it. It makes you feel like you're being pushed to the outside because you're really being pushed in. But since you can't hold it tight enough, you end up going in a straight line, and you end up ultimately catching up with the end of the bar, giving you the perception that you're being pushed to the outside again. Make sense? Sometimes when you look at tire advertisements, they talk about centrifugal force. It's able to withstand high centrifugal forces and so on and so on and so on. It's misleading advertising because they know full well that centrifugal force doesn't exist. Okay? They just talk about centrifugal force because that's what they expect you, that's what they think you expect to hear. Everybody's heard of that before. Oh, withstands high centrifugal force. Must be a good tire. Better buy that one. It's misleading, but in the end, what they really mean is legitimate advertising. What they really mean by that is that, look, it can be going really, really fast and still not break up and still not break or still not blow the tire. Does that make sense? If I ask you to define centrifugal force, somewhere in there, you better put the term fictitious or fictional or fake or pseudo force that pushes you to the outside of the circle. It's caused by inertia. Your inertia taking you in a straight line in combination with the centripetal force pushing in. Remember, anytime you have a force acting in one direction, you always have a pseudo force, a force that you feel but doesn't really exist, acting in the opposite direction. You can always come back to that example of me sitting at a stop sign getting hit from behind. It feels like I'm being pushed into my seat, but I'm not. I'm being pushed forward. First time I ever flew in an airplane, I was 13 years old. I remember I was flying by myself. Parents weren't with me. We're taxiing out at, I don't know, not very fast, right? You don't taxi out very fast. As soon as you make that turn onto the runway, and all of a sudden you're going from, let's say, 10 meters per second, 30 kilometers, 36 kilometers per hour, let's say, to a couple hundred kilometers per hour in a matter of a couple seconds, you feel like you're being glued into your seat, right? You're being pushed back into your seat hard, but you're not. It's your seat pushing on you forward really hard. It just feels like you're being pushed back. Does that make sense? Remember we talked about actual weight and apparent weight, gentlemen? In our last unit, actual weight and apparent weight. What force is it really that causes my weight? Well, no, my real weight is caused by not normal force. The opposite of that, right? Caused by gravity. What force do I feel? The opposite force, right? Although that one's not a pseudo force, but it's still the opposite force. All right, that's it for today. If you haven't finished up those 3 questions, let's get them finished up now. Then you can pack it up and we'll check these over tomorrow.